are algebra-based books, and this Halliday and Resnick book is sort of the go-to text for calculus-based physics. So if you want a textbook, this is the one to go for. I'll probably have a couple extra copies. If you just want to borrow one, you can borrow mine for a period of time. Or you can get them pretty cheap. Any edition is okay, even like the very first edition. All right? Any questions about that business? About the outlay of the course and what have you? Go ahead and pencil in those exam dates. We'll have the exams in this room, and just like last semester, you'll have an extra 15 or 20 minutes, so you'll come in early, because I know that y'all would like to get here earlier, right? But I'll give you a little extra time on your exam. I have a class in this room right after here, so we're sort of bounded by that. All right? Any questions or concerns? No? I did this last semester. Let me start on the material series. I did this last semester where I allow y'all a time to interview me. You remember how we did that last semester? All right, so you know me for a semester, and so now I'll give you just a couple minutes to ask me questions that you'd like.
Are you on that?
I'm working on an engine at the seminary in New Orleans. Here?
How do you get on the Moodle thing?
I'm sorry, that kind of question. We'll deal with it. Okay? No, just send me an email. Alright? Well, I'd like Oprah. I did my undergrad at Mississippi State, and my master's and PhD were at UT Austin. Oh, in physics, and then at graduate school it was in astronomy. I studied star formation in graduate school.
You know any of the people in the physics department in that
I know a few, like I've worked with a few of them.
I can't remember exactly. His name is Gary.
Yeah, that doesn't ring a bell. There's a lot of people in that department. But, yeah. In a minute or so, a couple more questions you can squeeze in. These aren't particularly good questions.
What exactly is your union? Is it like a class specific? What exactly is it for?
Oh, this semester I'm taking the history of Christianity from the early church to the Reformation.
Oh yeah, we need some of that class.
I took the second part of that last semester, which is the Reformation of modern day. And so this is just sort of what has happened to the Christian church in that time period of, 1,500 years or so. And the second course is really fun. I'm taking it online though, is interpersonal relationships. Where we explore how to relate to one another. A couple textbooks to read, a couple papers to write, but no relating really. But apparently, like pastors, they often fail because they're not very good at talking to people. And so this course is supposed to help you talk. It's actually kind of fun. One more question. The singer.
Did you go see Untitled?
I did not. I haven't seen a movie in a long time.
You should go see it.
Yeah, okay. My mother-in-law gave us a, well, it's not at the theater anymore. We'll get it. Maybe on Amazon Prime. All right. Okay, well this first chapter is on gravitation. And really the main reason we're doing this is because it turns out that gravitational fields and electric fields are very similar. And so we're going to get into this semester a lot about electricity and magnetism. And a lot of the things that will apply to gravity will also apply to electric forces. So it's important now to sort of revisit some of those things that we've already studied and apply them to gravity. All right, so this is gravitation. And a lot of this is dealing with what Newton did when he was studying gravity and actually in his development of calculus. He developed this idea, or this law, Newton's universal law of gravitation. I think last semester we actually mentioned this, but we didn't really go into much depth with it. And this just says that two objects of mass experience a force between them. Just for reference, you don't need to know this, but Newton developed this one in 1665. And any idea how old he was when he developed this law of gravitation? Very good. He was 23, actually. Yeah. So, which typically for scientists is their peak time. So a lot of y'all are at your peak right now, like the 25 to 35 period. I've long since passed my peak, but so he was 23 years old. You don't need to know that, but I thought it was interesting. And he showed that the same force that causes an apple to fall, or whatever, also causes the moon to be attracted to the Earth. And while that may seem not very important, at the time it was quite important because people didn't really connect the motions in the celestial bodies to the motions that they saw on the planet Earth. And so to say that these were the same forces and the same law that governed how these things were attracted to one another was extremely important. In equation form, the law looked like this. You'll have this equation, by the way, on your equation sheet, that this force between two objects of mass is some constant, g, times the mass of the first object times the mass of the second object over the distance between the objects squared. Now when we get into Coulomb's law soon, in the next chapter, we'll see that the equation describing the force between electric charges is basically identical to this, that it's two charges divided by a distance squared. This is an inverse square law, because the force varies as the inverse of the square of the distance between the objects. So I have object 1, m1, object 2, m2. The distance between them is r, and they experience a force. So I have the force on object 1 due to object 2, and then the force on object 2 due to object 1. I think we talked about this last semester, but the magnitude of these forces, F12, is equal to F21. These two forces are identical. So when we think about this in terms of the Earth, right, we talked about this, how I have a weight of 700 newtons. That means that the Earth is pulling down on me with 700 newtons. And likewise, I'm doing what to the Earth? All right, I'm attracting the Earth as well. Right, so there is an equal force. So the Earth is pulling on me with a force, and I'm pulling on the Earth with a force. Also, likewise, there is a force between us, like in this room. It's very, very small. Like, say, for example, the force between me and Gary. The magnitude of that force is about the weight of a speck of dust. So it's very small, but actually in a lab it's measurable. Even in like an undergraduate lab, you can measure the force between two objects of mass, the gravitational force. It turns out that the electrical force, on the other hand, is much, much stronger, and we'll see that in the next chapter. All right, so we also see that the force is proportional to mass. So the bigger the mass, the bigger the force. And the force is proportional to the inverse square of the distance. All right, we sort of had that before, but now we're going to get into some things that we haven't seen. So, you okay with this? Can I go on? Yeah. Just a reminder, all the notes and stuff are on YouTube, so I'll post these screencasts to YouTube. I'm just using a little microphone here, so the audio is not real great, but I think it'll be enough for you. Like if you miss something in class, you'll be able to go back and get it. Did y'all use those last semester? On occasion or regularly? Really? And the audio was sort of okay? Okay, it should be about the same, unless I walk around a lot. All right. Okay, so Newton proved something called the shell theorem. You know, a lot of what Newton proved wasn't really about the physical world. A lot of what he proved was just through his invention of this new technique, this new mathematical technique. And what was the mathematical method that he created? Right, he invented calculus, and he was able to show then through this invention of calculus a number of different things, and the shell theorem is one of those. So Newton proved the shell theorem. And it just says this: a uniform spherical shell of matter attracts a uniform spherical shell of matter attracts a particle that is outside the shell, as if all the shell's mass was concentrated at its center. So in short, let's say that we have this shell of matter. We had this hollow sphere, for example. This is a hollow sphere. It looks like a ring, but imagine in 3 dimensions. It's a hollow sphere. And then I have another mass over here, M. It turns out that, let's call this hollow sphere having a mass big M. It turns out that this is identical to having a mass M, little m, and then another particle that mass big M. So we can say that this scenario is identical to this scenario. And that was a shell theorem. This allows us then, when we're looking at the Earth, we have this huge planet Earth. There's Earth, North America, Europe, South Africa. And then we have an object that's sitting on top of the Earth. This is a mass little m. This is a mass big M. It turns out that we can say that this is the same as a particle with mass m and a particle with mass big M. And it's not obvious that that should be the case, that these two scenarios should be the same, but Newton showed that this was true. The way he did this, in short, I'm not going to do the derivation, you can go and look it up. It's pretty simple. You're just integrating over a volume, or over this spherical shell. Can I go down from here? In a way that we've done this last semester, and you'll see it again. We'll do some more volume integrals later in this semester. But he basically took a shell. Right, this is our spherical shell, and he took a point, and he showed that if he integrated over all these points, the force, right, you'd get all these force vectors. If he integrated over all those force vectors, then it would be the same expression as just taking the whole mass down at the center of the shell. So if you're interested in that, you can look up this derivation. It's only about 5 or 6 months long. But it's just a volume integral, integrating over that volume, over that object, and calculating what is the force for each differential element, and then adding those all up together. Remember how we did that last semester? I think, I don't know, what did we do that for? Yeah, we did it for moments of inertia, yeah. So we'll do that again this semester when we're calculating electric fields in chapter 2. All right? So on your faces, like, I'm not really seeing the magnitude of the importance of this, but this was a really big deal for him to not only invent calculus, but then also to prove this physical fact that we could say that these two objects, we can say that they are just point objects, point sources. Okay, let's see. We can also use Newton's universal law of gravitation to figure out what is the force due to several particles. So remember, our universal law of gravitation is G m1 m2 over r squared. And by the way, I don't think I gave you G. You don't need to know this. I'll have it on the equation sheet. But it has a value of 6.67 times 10 to the, I think it's 31. No, minus 11. Excuse me. 11 Newton meter squared per kilogram squared. That's just a unit that's determined empirically or experimentally. So they measure the acceleration between two objects of mass, and then you can calculate what this gravitational constant is. You can also, we'll see how this is also related to the acceleration due to gravity. So you can measure this by measuring the acceleration due to gravity as well. There are actually experiments that are ongoing to measure this to very great accuracy. There's one experiment out in West Texas at McDonald Observatory where they shine lasers up to the moon, and then it's reflected back. And by that, they can measure the acceleration of the moon as it orbits around the Earth, and they can very accurately measure this acceleration due to gravity, which tells them a number of different things. We'll probably talk about that a little later. How does it come back, the laser? Is the moon just very reflective? Oh, that's a good idea. Like maybe like the gravitational field of the moon makes it come back. Yeah. No, it's not big enough. What would be the obvious answer? What's that? It reflects back, but I mean, what do things reflect off of? Yeah, there's a mirror up there. So when the astronauts went to the moon, they left the mirror on the moon so that they could perform experiments like these. And it's actually, I think we might have talked about this. You know, in surveying, there's a type of mirror where if you shine light on it, it comes back directly that same path. I don't know what it's called. A prism mirror? Yeah, well, anyway, so it's that type mirror where they shine a laser up to the moon and then it comes directly back on itself. And by measuring the time that it takes to go from the Earth to the moon, they can measure how fast the moon is moving. In fact, how fast the moon is falling towards the Earth. Because as you know, the moon is always falling towards the Earth. It just falls in a circular path. Or not quite circular. We'll get into that soon because we're going to get into orbits in this chapter as well. Okay, so we can determine what is the net force on an object if we have, say, a collection of particles. Just do a quick sample calculation. We've done similar to this. This is just a simple vectors problem, but here we're applying Newton's universal law of gravitation. And we'll see it again in chapter 2, I guess. I'm calling this chapter 0, by the way. But when we get into the workbook in chapter 2, where we're actually calculating the force and the electric fields due to charged particles, we'll do these type of vector calculations again. So we did this last semester, but it's coming back this semester as well. Let's say that I have 3 particles. I have a particle M1, I have a particle M3, and a particle M2. M3 and M1 are separated by a distance 2a, and this is separated by a distance a, and the values here are M1 is 6 kilograms, and M2 and M3 are both 4 kilograms. And the distance a here is 2 centimeters. But of course we'll be in the SI system, so 2 centimeters, I move that decimal place over twice to the left, so it's going to be 0.02 meters. All right, we will be using the SI system, so if you've forgotten your metric prefixes or the units and stuff, I suggest you go back and look back over that. But you will have to do unit conversions just like we did last semester, changing those metric prefixes, changing into the SI system. So don't forget that we use the MKS system in physics, whereas in chemistry you often use the CGS system, but we use the MKS system, meters, kilograms, and seconds. All right, so I want to know what is the force on particle 1. And I want to know that in vector notation. I can just sketch it out like I've done before. I know that there are 2 forces acting on particle 1. There's the force on particle 1 due to particle 2. What is the direction of that force? what is the direction of the force on particle 1 due to particle 2? There's a force between these two particles. There's a force on this particle and a force on this particle. What's the direction of the force on this particle?
It's the larger mass.
Right. Not even towards the larger mass, but it's just towards the other mass. Right? So there's a force down, there's a force up. They're equal. So my force is up for particle 1. So I'm going to call this force on particle 1 due to particle 2. What is the force on particle 1 due to particle 3? What is the direction? Left, right, up, down. It's to the left, right. These two particles are attracted to one another, so there's a force in that direction. So this is the force on particle 1 due to particle 3. Right? I can go ahead and calculate the magnitudes of those. The force on particle 1 due to particle 2 is equal to g times the mass of particle 1, which is 6 kilograms, times the mass of particle 2, which is 4 kilograms, divided by the distance squared, that's 0.02 meters squared. Putting in g there, and it turns out that this is equal to, let's see, force on particle 1 is 4 times 10 to the minus 6 newtons. All right, and then we can do a similar thing for the force on particle 1 due to particle 3, where instead of using particle 2's mass, we use particle 3's mass, and that's going to be 1 times 10 to the 6, negative 6 newtons. All right, just coming back to y'all, remember we've done similar things, and we're going to do it a couple more times, dealing with electric forces and also electric fields, which we'll get to soon. All right, so now I have this this M1 particle. I have a force that is 4 times 10 to the minus 6 newtons. And then I have another force that is 1 times 10 to the minus 6 newtons. I can draw them like that. And then I want to know then what is the resultant force. What is this force? And that's F1, our net force, F1. In order to find that, I use the Pythagorean Theorem. The magnitude of F1 is the square root of 4 All right, y'all should be good at this by now, but if you're not, just come see me and I can go over it with you in my office. And then it turns out that's equal to 4.1 times 10 to the minus 6 newtons. And then, of course, this is a vector, so I need what type of information? Not just magnitude, but also, right, so I need to know the direction. And on your exam, I'll ask for the direction. I'm going to give this angle. And you can use your trig functions. I have the opposite and adjacent sides. So it's going to be the inverse tan of what? 4 over 1 or 1 over 4? We're in class, Joe. That's okay. 4 over 1 or 1 over 4? Well, tan is what? Opposite over adjacent or adjacent over opposite? Opposite over adjacent. So what's...
4 over 1.
Right, the opposite side is 4. So it's 4 over 1. You can write the 10 to the minus 6, but they cancel. So it's the inverse tan of 4, which turns out to be 104 degrees. And this is above the negative x-axis. Okay? We're going to do some vectors, really just in the first couple chapters. Sort of simple vector addition like this, we'll see. But hopefully those will be easy problems for you, easy points, right? Y'all okay on vector addition? Okay. Guys, I don't have the homework for this chapter yet. Hopefully I'll have it by Friday or Monday, but I'll have some practice problems for you. I'll try to make some videos, or at the very least I'll just give you the solution, and then if y'all have problems with it, we can go over it in class, okay? But I'll try to make some solution videos. Y'all use those? The homework solutions? Yeah. All right, I'll try to make that for you. As I said, I'm sort of making this up as we go along, like working on my notes and trying to develop other things for it as well. But I'll have those homework problems for you as soon as possible. I know that y'all are very eager to get them, right? Yeah, okay, good. All right. Okay, so now let's look at gravitation near the Earth's surface. We know now that F is equal to G mm over r squared, where this is the mass of the Earth, and this is the mass of you, or the object, or the apple, or whatever it is. We also know, through Newton's observations, and his second law of motion, that the force is proportional to our acceleration in this way. F is equal to ma. And so I can combine these two, and I can say that A is equal to F over m. Right? If this is F, then I get this expression. I get G m over r squared. And this is going to be our gravitational acceleration. All right. I also want to point out here, this expression right here, we're going to see a very similar expression later when we get into electric fields that's going to look a lot like this. So I just want to mention it here. You probably won't, you're not going to see this on the exam for this chapter, but I just want to go ahead and present this idea of field lines, or lines of force. This acceleration samples the gravitational field around an object. So if that acceleration is big, that means that the gravitational field is big. If that acceleration is small, that means that the gravitational field at that point is small. Right? Don't write this down, just listen, because we're going to see this again later. So imagine that we have the Earth here. There's North America, South America, Europe, Africa. I can imagine that there are these lines coming out. These are field lines. They measure the strength of the gravitational force. And where those lines are close, that gravitational field is big. And so where is the gravitational field the biggest? Far away or nearby to the planet? Where are the lines the closest? The blue lines. Near, right. They are, what's the word when they spread out? Diverging. Divergent. That's a movie, right? They're divergent, right? They diverge, so as they go far away, they get further apart, and the gravitational field actually decreases in strength. That means that the gravitational force decreases in strength, which we know because of this 1 over r squared dependence. That as r increases, the force goes down. All right, so if I have an object here, it feels an acceleration that's big. But if I have an object here, it feels an acceleration that's not so big. All right, and that's expressed here that the forces decrease, and so that acceleration also decreases. Again, don't worry about this right now because we're going to see it later with electric fields. I just want to sort of introduce this concept of fields, but don't write this down. We'll see it again very soon in just like a chapter or two. All right. Okay, so going back to this idea, AG here, we're going to call the gravitational acceleration. And that's going to be in contrast to G, which is the free fall acceleration. I'll show you what I mean. You might think those are the same, but they're actually a little bit different. And all along, we've always assumed that the gravitational acceleration equals the free fall acceleration. We've always assumed them to be what? 10 or 9.8. We'll say it's 9.8 right now. So we've always assumed them to be the same, but in fact they aren't the same. They're different by a little bit. And there are three reasons why this is the case. So these are not the same. For three reasons. All right, number one, Earth's mass is not uniformly distributed. All right, so the gravitational acceleration at one point on the Earth might be different from the gravitational acceleration at another point on the Earth. We talked about this, I think, in the lab when we did the pendulum experiment, or most of you were in my lab. But there's a NASA mission called GRACE. Ever mentioned this mission to you? No, GRACE is a NASA mission. It's basically a pendulum up in the air that orbits around the Earth, and it just measures the period of that pendulum, which allows you to measure the acceleration due to gravity. And that changes depending upon where the object is, because this mass of the Earth is not uniformly distributed. So that that acceleration due to gravity might be measured different, say over a mountain range, than it would over the ocean, or over an oil deposit as it would over just dry land. And so they can use this information to map out what's under the surface, the mass distribution of the Earth, which is very useful when you're trying to define water tables, oil, underground type things, and also just trying to study the structure of the Earth. So the Earth's mass is not uniformly distributed. The second reason is that the Earth is not a sphere. It's actually sort of, I think it's called, what's it, oblate, I think is the right word, where it's squished a little bit. It's a little bit bigger at the equator than it is. Like an ellipse, yeah, but like an oblate sphere, I think, which is where it's just squished. I think that's the word. Don't write that down, but I think that's the word. It's not exactly a sphere, and so the shell theorem doesn't apply. By the way, you could see on the exam just a short answer question about, say, for example, the shell theorem. I'll give you a little extra guidance on this chapter later about what to expect on the exam, but you'll likely see just sort of a short answer about something. And then also, the Earth is rotating, and this is really the biggest deal. The Earth is rotating, and hence everything on the surface of the Earth is rotating. So because of that, we have what type of force working on objects that are rotating? A centripetal force, right. So we have a centripetal force. So we have a centripetal force. All right, so those are three reasons. The Earth's mass is not uniformly distributed. The Earth is not a sphere, so the shell theorem doesn't apply. And the Earth is rotating, so we have a centripetal force. So those are three reasons. The main reason is number 3. And I'm just going to sort of start on it. I'll just sort of get it set up, and then I'll show you next time how it comes up. So let's imagine that we have the Earth. This is the North Pole, so we're sort of looking at it from above. This is the North Pole. This is the equator. We have a distance r here, and let's say that we have a box or a crate or whatever. It's rotating in this direction, right? The Earth is sort of rotating around. You're looking at the Earth above from the top, and so it's rotating in that direction. On this, I can draw a force vector diagram. I have what force is acting on this box? Okay, I have the
gravitational force on the center, and then you have centripetal.
Okay. I have the weight of the normal force. All this Fn. this weight is going to be m times the gravitational acceleration. That's ag. That's as opposed to its free fall acceleration, which is how it falls when it's in free fall. So this is that gravitational acceleration. And remember, that ag we've already found is equal to gm over r squared. Okay, that's our gravitational acceleration. And then, how does our centripetal force come into play here? How is it represented? What is our centripetal force? Well, I'll just tell you this. All right, we have a centripetal acceleration. So this object, even though it's not moving up and down, it is accelerating in that direction because it's moving in a circular path. All right, so I can write Newton's second law. The sum of the forces equals ma. That's the normal force minus that mag, that weight, is equal to ma, which is going to be mar. I think we'll pick up there next time, and we'll finish this little derivation, and then we'll work through some sample problems, and probably a couple more days on this chapter. We're going to do Kepler's laws. I think we'll probably do Gauss's law as well regarding fields.